Hi. In the final segment of this topic, we shall use the properties we looked at in the previous segment to define different kinds of relations. In particular, we shall talk about relations representing notions of equivalence and order. A binary relation over a set A is called an equivalence relation if and only if it is reflexive, symmetric, and transitive. For example, let us look at the regular equality between things, at the divides relation, and at the coprime relation. Are those equivalence relations? If yes, why? If not, why not? Equality, yes, it is an equivalence relation because it is reflexive. A is always equal to A. It is symmetric. If A is equal to A, then A is equal to A. And it is transitive. Divides is not an equivalence relation because it is not symmetric. 2 divides 4, but 4 does not divide 2. Being coprime or relatively prime is also not an equivalence relation because it is neither reflexive, 3 is not relatively prime to 3, nor is it transitive. 2 is relatively prime to 5, 5 is relatively prime to 6, but 2 is not relatively prime to 6. A concept closely related to equivalence relations is that of a partition. Given a set A partition of A is a family of pairwise disjoint sets, such that the union is equal to A. You can think of a partition as a complete subdivision of A into smaller subsets. Every element of A is an element of exactly one set in that partition. For example, are these families of sets partitions of the set A? In the case of the EU citizens, no, since an EU citizen may be a citizen of more than one country, and so that means that the BI are not pairwise disjoint. The atoms are partitioned by the elements, since every atom is an atom of exactly one element. The natural numbers, however, are not. First of all, the set of multiples of different primes are not disjoint. And without the primes themselves being in them, their union does not actually include all natural numbers. If we have a set A and an equivalence relation over it, we can actually use it to compute a partition of A. First, we introduce the notion of an equivalence class. For any element of A, its equivalence class under that equivalence relation is simply the set of all elements of A that are equivalent to it under that relation. We write the equivalence class of A as A in square brackets, often with the name of the equivalence relation added as an index. Note that there are various ways of writing this in the literature, but the one above is the one we shall be using in this course. With this, we can define the notion of a quotient set of A divided by an equivalence relation as the set of all equivalence classes for all the elements of A. The connection now to partitions is that the quotient set is a partition of A. Also, it is always true that a given partition of a set, any partition of a set, can be used to define an equivalence relation such that the partition is its quotient set. What this really means is that equivalence relations and partitions are basically just two ways of representing the same thing. If you would like to study this in more detail, please take a look at section 254 in the textbook. We will now turn to another class of relations called orders. Orders are relations that, well, order the elements of a set according to some notion of size or magnitude. A good first mental model for orders are the ordering relations on numbers or the inclusion relation on sets. We say that a binary relation is a non-strict partial order if and only if it is reflexive, antisymmetric, and transitive. Are these relations non-strict partial orders in the above sense? Check against the properties in the definition. And these are the answers. Check them by checking whether they have the properties required in the definition or find counterexamples when they don't. If you combine a set with a partial order over it, the resulting pair is called a partially ordered set, or poset for short. For example, n plus under the divides order is a poset, as is any power set under set inclusion. A strict partial order is similar to a non-strict one, except that it is irreflexive. That is, it never relates an element to itself. Think of less than as a strict version of less than or equal to, or proper set inclusion as a strict version of set inclusion. By the way, we do not specifically need to require asymmetry or anything of the kind, because asymmetry is actually implied by irreflexivity and transitivity. Think a little bit about this. Convince yourself that this is true. So far, orders were partial, which means that not every pair of values would have to be related to each other by that order. We already had run into this concept when we discussed set inclusion. Given two sets, neither might be a subset included in the other. A non-strict total order over A is reflexive, antisymmetric, and transitive, just like partial orders, but in addition, it is required to be total. That is, any pair of elements of A are related to each other, one way or the other. Are these relations non-strict total orders? These are the answers. Check against the properties in the definition. Finally, suppose we have a relation R over some set A. But we need something that is pretty much like it, but transitive. We need a transitive version of R. That's what the transitive closure of R is. It is the smallest relation in terms of the pairs contained in it that includes R and is transitive at the same time. Given R, we can compute it as shown here in the following steps. First, we start with R itself and call it R0. Then we iterate. At every step, given in Rn, we compute the next relation, Rn plus 1, by taking Rn and then adding a set that contains all the pairs AC, such that when Rn contains a pair AB and another BC, AC is contained in that set. In a sense, you can think of the transitivity rule implying or demanding the existence of AC when both AB and BC are present. In this step, we just add all these implied pairs to Rn if they weren't present already. In this iteration, we basically compute infinitely many Ri. In the final step, we just throw them all together into one big union. That is our transitive closure. We note the transitive closure of a relation by adding a plus sign as an exponent. Let's look at an example using the bow tie relation among European countries again. Think about what the transitive closure of the bow tie relation means in this context. Recall that the relation itself represented that two countries were connected by a land border. That is, one could walk from one into the other. What does the transitive closure of bow tie represent? What does the result of iterating this relation over itself again and again, adding implied edges or pairs to it? What properties does it have?